If you take a 3D sphere and force it to lay perfectly flat, the surface will physically tear and stretch. Every two-dimensional map of the world requires a mathematical compromise. Cartographers must choose exactly how they are going to warp reality. The math gets even more complicated because the Earth is not a perfect sphere. It bulges at the equator, making it an oblate ellipsoid. Proving this shape required staggering manual effort. In the 18th century, surveyors traveled across the globe with heavy brass instruments like these to meticulously measure arcs of the meridian across different latitudes. Projecting that specific oblate shape onto a flat rectangle guarantees a distortion of the surface geometry. Mapmakers have to pick their poison. They can preserve the true relative area of the land masses, or they can preserve the exact angles and shapes of the continents. They cannot do both. Walk into nearly any classroom, watch a news broadcast, or open your phone, and you will see the Mercator projection. It is the default way we visualize our planet, but that familiarity hides a massive distortion. The Mercator map radically inflates the size of land masses closer to the poles, like Europe and North America. Look at Greenland. Here it appears equal to Africa, but lay Africa over Greenland, and reality clears. Africa is 14 times larger. Shrinking the equator while ballooning the north minimizes the global south scale, training us to see these continents as less prominent. By accepting the Mercator map as the standard, we trade the reality of global geopolitical scale for a familiar, clean set of north-south grid lines. Gerardus Mercator didn't design his 1569 projection for classrooms. He built it to solve a mathematical problem for maritime navigators. They relied on loxodromes, paths of constant compass bearing. Mercator's math allowed sailors to plot that bearing as a perfectly straight line across an ocean. To keep those lines perfectly straight, Mercator had to space the latitude lines increasingly further apart as they moved toward the poles. This visual matrix shows exactly how different maths handle these compromises. Notice that Mercator scores perfectly on preserving local angles and shapes. That exact trait led Google to adopt a variant called Web Mercator in 2005. It ensures a city block looks like a perfect square, and a 90-degree intersection displays exactly as 90 degrees. This framework is computationally light, allowing digital mapping apps to load square map tiles seamlessly as you swipe around your phone. But zoom all the way out, and the macro-level flaw is obvious. We update the matrix to show both versions of Mercator completely failed to preserve equal area across the globe. Mercator is a brilliant mathematical tool if you are navigating a city grid or sailing across the Atlantic. It is disastrous if you are trying to understand macro-level global proportions. Activists recognized this Eurocentric distortion and pushed back. Their most famous countermeasure is the Gall-Peters projection. Looking at our comparison matrix, the Gall-Peters map forces a perfect equal area mathematical representation, guaranteeing developing nations are shown at their true relative size. But forcing equal area onto a rectangular grid carries a severe aesthetic penalty. The matrix updates, showing the shapes of the continents are radically stretched and elongated, creating high visual friction. Because the math looks so unnaturally warped to the human eye, the general public and major educational systems largely rejected it. Securing political fairness and scale fails if the resulting map is too visually jarring for people to actually use. The modern solution arrived in 2018 with the publication of the Equal Earth projection. Adding equal Earth to our matrix shows how it solves the problem. It uses pseudo-cylindrical math to preserve equal area, avoiding extreme vertical stretching. Instead of a harsh rectangle, it mimics the pleasing curved edges of compromise maps. The layout feels familiar and balanced. That familiarity has fueled the Correct a Map campaign, where scientists and activists are using this specific projection to decolonize the depiction of physical space. It has rapidly gained institutional momentum, earning endorsements from major scientific bodies like NASA and strong backing from African activist networks and the African Union. It still requires a mathematical compromise. The angles and shapes near the outer margins warp slightly, rendering equal Earth entirely useless for nautical navigation. But for global representation, equal Earth successfully balances the mathematical honesty of true continental scale with the visual appeal necessary for public adoption. Labeling a map as objectively good or bad misses the point. You cannot evaluate a tool without knowing the specific task it was built to perform. This flowchart
illustrates a decision framework based strictly on user goals rather than cartographic purity. If you are a developer building a GPS app, managing supply chain logistics, or routing local navigation, you must adopt Web Mercator. You need street-level shapes and routing angles to remain perfectly intact on the screen. As a developer, the trade-off is accepting that your zoomed-out global interface is functionally misrepresenting scale. On the other hand, if you are an educator teaching geopolitics or a data analyst mapping global demographics and climate trends, you must adopt Equal Earth. This ensures your data density isn't skewed by the artificially inflated size of northern countries. Finally, if you just need a general aesthetic representation of the world without strict data plotting or navigation, you can comfortably rely on a compromise map like Robinson or Natural Earth. There is no one true map. By abandoning that myth, we are empowered to use Mercator to accurately find our way, and Equal Earth to accurately understand our place in the world.